So a few months ago, a couple of us were sitting around talking about projects and things that we build, and we got to talking about components, individual components that go into a project. And someone brought up, and I think it was Jim, he brought up the point that how many people in the ham community, particularly new members, know what the components are or why there are so many different types of components. So we decided to start a series, and we're going to start tonight with capacitors, of actually, Jim is going to give this first presentation, actually coming up and explaining to us why there are so many different kinds of capacitors and why they're used in different applications, particularly in ham radio.
We're going to be doing passive components, capacitors, resistors, inductors, and then maybe some other passive units initially in this little bit of a program we're going to do. I'm WA8 MPA, licensed in Ohio in 1964. So I've been at this quite a while as an amateur radio operator and enjoyed the hobby tremendously and enjoyed this club very, very much so. And I've been a member of it for about 12 years now. Anyway, this is a 20,000 foot view, which means we're not going to get into a lot of math. We're not going to get into a lot of theory, but we are going to get into some, and we're going to have some fun times with it. What is a capacitor? Here's our definition. I don't need to read all this for you, but you notice the equation at the bottom, C, capacitance, is the charge, the Q, remember that from maybe high school physics, divided by V, and it's in farads. And we'll get into farads a little bit later on. Most of you know about microfarads, nanofarads, microfarads if you're a little bit older, picofarads if you're a little bit newer. But anyway, this is one of the things that we're going to get into a little bit. Well, what does a capacitor look like? This is what you were taught probably in high school. It's two conductors, metal plates, separated by a dielectric, and you're putting charge, Q, little charges on the plate on the left, and you're pulling them off on the right. And you can see that the things that go ahead and determine what kind of capacitor you have, or the capacitance, is the area of your plates, the distance between the plates, and what is that stuff that's in between the plates, the dielectric as it were. Okay, this is one of the two definitions we're going to get into. This is dielectric permittivity. It's got the little epsilon symbol. It's the ability of a material to hold a charge. Capacitors are often, as an analogy, said to be like batteries. They can hold a charge, but the charge is not chemical. The charge is an electrostatic field. It's the Q that's being going on here. And then there's a dielectric constants depending on that material that's in between those plates, and it varies around. This is some of them. What I wanted to point out here that's kind of important, that is if you have an air variable, we have 3 of them on the back table, it's a little bit above 1, just barely. And if you look down at the bottom of the list under vacuum, you see that it's a 1 with a whole bunch of zeros on it. So air variables, vacuum, very, very close. And then you get into other materials. Glass, for example, when I was in high school, we would make capacitors using foil and glass, put the foil on either side of the piece of glass, put a wire to it, hook it up to our Tesla coils, and shock everybody in the glass with that kind of activity. But those are some of the values. You notice Mica on the left, 4 to 8, pretty good. 4 times better than air, for example. These are some symbols, and ignore the one in the center with the short. But on the left side is our traditional symbol for a capacitor. The one in the middle is polarized. It's got a plus sign on it. And the one over on the far right is a variable capacitor. Again, we have about 4 of those on the table in the back. If you have an amateur radio piece of equipment, I guarantee you have probably more of this component in there than any other component, including resistors. Capacitors are just ubiquitous. They are the #1 component used in electronic equipment, and especially our amateur radio equipment. What are the units? Hey, we got microfarads, 10 to the minus 6, nanofarads, 10 to the minus 9th, picofarads, 10 to the minus 12th, and then, of course, the daddy of them all, the farad. And again, the farad is a very, very, very large value. Here's some of the things you can find in your ham gear, whether you've got a little HT, an HF rig, or whatever. You'll notice you got electrolytics in the upper left. We've got some ceramics and some chip capacitors. All of these are back on the table. We've got some other capacitors through here, and our little air variable, and some little trimmers. So this is what you're going to find in amateur radio gear. Here's a little closer look at some of them. You probably recognize them. These are our little chip capacitors. We're starting to see more and more and more of these in our gear. And thanks to Brian, I have 4 of them back there that are much smaller than a grain of rice. In fact, they're much smaller than just about a pencil point. And if you can see them, I'll be amazed. I put a magnifying glass back there. So you get to look at them up close. Most of us are wearing glasses, and if not, we need them. So you would need those to see those little capacitors. And they come on a roll. The roll is back there, and you can get, I don't know, Brian, how many in a typical roll?
10,000.
10,000. So 10,000 of those on one roll that looks like a, 8 millimeter film.
A few left.
Yeah. Yeah. Here's an example of what the sizes start to look like. Now, the scale on the bottom is in centimeters, so each little hash is a millimeter. Okay? So you see the electrolytic on the lower right, and above that, you see how they're getting smaller and smaller and smaller and smaller and smaller up to the top there. The ones we have on the table back there are not the smallest ones. You can barely see them, but there's one more size that I'm aware of down below that. And that just makes it very difficult. If you sneeze when they're on your workbench, they're going to be like dust all over the room. I wanted to pretty much concentrate on electrolytic capacitors tonight because we have those in our power supplies. If you've got a 13.8 volt power supply, you're supplying your HF rig, you're supplying, your UHF or VHF equipment, whatever you got, chances are, whether it's a linear supply or it's a switching supply, it's got electrolytics in it. And they're commonly used for filtering in our power supplies. They help to reduce the ripple. They're used in switching supplies too, Amatron and some others that you can get. They are very critical components, but they have a usable shelf life. They probably are the shortest shelf life of all the capacitors in the family. If you have an old piece of equipment that you had 20 years ago and you pull it out and you're trying to use it, chances are excellent that the electrolytics in it are not up to snuff right now. In fact, maybe totally dead. And that's because they are electrolytics. They have a liquid in them. And that liquid tends to dry out over time, especially if they're abused. It will really dry out. And sometimes it's very dramatic when you first power it up, which is why they usually recommend that if you have an older rig, you put it on a reactor or transformer, you bring it up really slow, let the tubes and those electrolytic capacitors sort of get back in the game. Otherwise, you're going to cause yourself some problems. The leakage current on even a good electrolytic is fairly high. Relatively speaking, it's the highest in all the families. So that's sort of how they sort of self-discharge. You charge up an electrolytic, if you sit it on the shelf for months, it's probably going to discharge itself like a battery. Okay, looking at capacitors, what are they realistically? This is an example of what's called two-level modeling. You see a capacitor that's ideal in red. There's a component of resistance across it that's in red. And then there's the resistance of the leads. It's always got wire going to it. That's in blue. And there's always some inductance associated with that wiring. That's in blue. So that's an example of a pretty decent model if you were doing design work that you would want to work with. Simplifying it down to where we are in amateur radio, you've got an ideal capacitor and an equivalent series resistance, ESR. And that resistor is what is going to kill what's going on in an electrolytic capacitor. You would like to have that as the lowest possible value, because think about it. If you have current flowing through that capacitor, what's that resistor going to produce inside that can or that container? Heat. And the heat and a liquid. What happens when you boil water? Well, you got an electrolytic in there, maybe rated for 80 degrees or 90 degrees centigrade. You keep heating it up and it's going to go away. It's going to dry up. So that's why we do have a meter back there, and we're going to show you how to use an ESR meter so you can figure out what does an electrolytic capacitor typically have for an ESR. ESR values are important. You want them to be as low as possible. You can read what's on the slide. They are temperature dependent. Your electrolytics are sitting in the car. It's 130 degrees. They're rated at 90 degrees, or they're in your equipment. The fan goes out on your switching power supply or your linear power supply. Those capacitors are not going to like that. They just are not going to be tolerant of excessive heat. Here's a graph, and it shows in the yellow Those are aluminum electrolytics. The Al is aluminum. You see what happens? The ESR is almost 1 ohm at minus 60 on this scale in centigrade. It does come down, and then it's sort of levels off a little bit. The hybrid form, it's not a liquid. It's more of a paste or it's a poly. And it's an electrolytic, but it's not the watery kind. So it has a little better shelf life in that sense. I wanted to just show you this graph real quick. Over on the left, pick out the 100 microfarad capacitor on the left where it says capacitance. Let's say it's your 16 volt power supply that you've got running your equipment. You notice it's 0.7 ohms. That's the ESR value. So it's not quite an ohm, but it's 0.7 ohms. If you were to go to a 1000 microfarad capacitor for that same voltage, it changes to a 0.15. So this is a typical chart. If you buy a Chinese ESR tester, they will sometimes stick this chart on the outside of the piece of equipment, and they expect you to look it up, voltage versus capacitance, to see what would be passing or failing. That's how they do it. Okay, some fun facts. Price-wise, Brian, how much did you pay for your spool of capacitors? Okay, here's an example. I've got it up in red. Kemet is a big manufacturer of capacitors. They're real high precision stuff, like 1%, which is a great tolerance value for caps. They want $2.50 each of those in lots of 2,000. That's pretty pricey. On the other side of the scale, they want 0.026 cents in quantities of 10,000 for a little sloppier sort of tolerance that they have. And that's just what it really works with. And down at the bottom, there's a different little packaging. That one is really nice. Those people are proud of that device. They want $3.44 when you buy 1,000 of them. So you're going to pay $3,400 for a roll of 1,000 of those suckers. And a roll is very small back there. They can be very expensive, but it goes to tolerance. In amateur radio, the most accurate caps that we play with are Class 1 ceramics. They're the most cost-effective. They are stable. You probably have more of this kind in your equipment than just about anything else right now if it's an older piece of gear, especially if it's not, built on the chip capacitors. They're great in oscillators, filters, and the audio industry loves them. This is an example, and I've got this in the back. This is what it looks like looking down on the top of the ceramic capacitor, and it's been cut. So you see the ceramic dielectric in the center. You see the wire leads sticking up at us on either side, and they're attached like with a little bit of solder to the both sides of the ceramic, and then you've got the plastic enclosure that protects it. So that's what it looks like inside, and I've got one back there chopped like that, so you can take a look at it. Ceramic caps, the Class 1s are highly stable. They're a little more expensive. They're very accurate. If you were going to DIY something and you wanted to build a project, this is where you probably want to go. They're not that expensive, and they will last a long time. They're very stable. The problem with them is they don't go up in real high values. You're kind of limited in the family that you can get with them. Mechanically, they are sometimes a little bit on the weak side. You can break them. And that last one is really kind of funny. They can be microphonic. I have worked on equipment where you can tap the capacitor and you can hear it ringing in the audio on the piece of gear. So they can act as microphones if they're really defective. Next up is tantalums. Tantalums are kind of a type of electrolytic. They are very popular. They're popular military applications, medical. They're very stable. The audio industry really likes these things, but they are expensive. You're talking 3 to 5 times more expensive than the equivalent value in a ceramic. And the one big drawback about them is if you get that polarity wrong on that tantalum, there is no forgiveness. It is going to blow up on you. An electrolytic, sometimes, if you're down below the working voltage, you can get away with putting it in wrong for a few seconds. Not going to happen with a tantalum. It's a mini bomb. It's just going to go off, which, in some cases may not be in a circuit that you want to have near things that otherwise could go up to in flames. Here's what one looks like. Those chip tantalums, if you notice, it's got the plus side, the anode, over on the left, and on the right-hand side, it's got the cathode, and that's the construction. You can read what's inside that. That's that teeny little chip that's back there. That thing is barely visible to see. If you put that in wrong, what's going to happen? Boom. Yep, that's exactly what's going to happen. This is one of those cut in half. That's what it looks like on the inside. There's a picture of it before it was sacrificed down at the bottom. Up at the top, you can see slicing through how the leads go and the material itself, the dielectric, and how it's packaged. So that's what our tantalums look like. And they are fun to work with. They are just a lot of capacity in a small package. They're good-looking little devices. And again, if you treat them right, they're going to work for you right. Silver micas. Now, back 20 years ago, these things were the kings. You know, silver micas were expensive, but boy, were they stable. If you had a piece of Collins gear or something like that, the oscillator circuits, the circuits that were really critical, they would have a lot of silver micas in it. They are stable. You can get them with very low tolerance. They're very temperature, range, within their range is working quite well. And they are used in a lot of good applications. Polys are pretty popular now. You can see I've got some of those in the back that you can take a look at. They're used in analog circuits primarily. You don't see a lot of polys in digital circuits so much anymore, but a lot of them are in the analog circuits. They are higher costs for the same capacitance, the same voltage, the same parameters. You're looking at about twice the money, but they are low leakage. And if that application is important to you, that's going to be where you're going to pay for it. The one bad thing about them is they don't forgive when you go over their working voltage. If they were rated at 30 volts, you can go 15%. You can do the math on that. You go above that value, they're going to be toast. A lot of the other capacitors are much more forgiving. If you go over top of what their working voltage is, they'll let you get by as long as you don't stay there. This is the inside of a film capacitor. Got one of these back there chopped up. You take a look at it. Looking down from the top, can you find the two wire leads that you can see in the picture? And that's wrapped over and over and over and over and over again, and then encased in the protective plastic. So that's the capacitor. Okay, here's a fun fact. How big is 1 farad? When I was growing up in school and everything else, a farad was nobody would go near a 1 farad capacitor. You wouldn't even think that they existed. They do nowadays. If you were to form a capacitor with 1 millimeter of spacing between the plates, okay, remember what a millimeter is, and you wanted it to be a 1 farad capacitor, it would be 10 kilometers by 10 kilometers square. Those are these two plates. That's how much a farad is, if you do the math on it. It's huge. That's why, no one ever bothered saying, hey, I want a 2 farad capacitor or a 3 farad capacitor. It didn't. It was physically impossible to create one unless you had a buku bunch of money. Okay, here's a 10 farad capacitor that you can buy today, probably in Auburn. If you are an audio buff in your car and you want to run your 2,000, 5,000 watt audio system and you want those bass notes into your, 20-inch subwoofers to really just sing out, that's what you would be buying. That is a 10 farad ultracapacitor. They're not cheap. And why do you need that kind of capacitance? Well, they want to drive those speakers. They want to drive them on the bass notes, and they want to be able to really, blow the windows out of the car. So there they go. Okay, this is one of my last fun facts to wrap this up. You remember seeing electrolytics with that little teeny triangular pattern in the top? That's a fuse plug. Many manufacturers will put that on their capacitors. So if that heats up because the electrolytic is dying or there's too much ESR in it, it's supposed to pop that out versus explode on your circuit board. So that's a fun fact. That is a fuse. That is basically a container that's supposed to just basically release the pressure in it rather than destroy things. Okay, that's it. This was a Tech 10. Wanted to try and keep it to about 10 minutes. Any quick questions? I've got all this stuff in the back you can look at, and during the break, we'll take a little bit of time. I want you to play with measuring capacitors, use the ESR meter, and with the magnifying glass, see if you can find the chips.
On that 10 microfarad, how would you bleed that off to work on it? Or 10 farad, I'm sorry.
I don't know. I would imagine having all those speakers, Turn it off, yeah. They've got to do something. They probably have, 4-ohm speakers in a car like that? Have you ever seen anybody driving down there with these big, 12-inch woofers on their back dashboard, just naked, pointed toward the front? Yeah. That's pretty amazing. And that's not the biggest one you can get either. They have 100 farad capacitors, supposedly, for your audio car stereo. The inrush current on that must be pretty phenomenal. I mean, you're looking, almost like a dead short for, milliseconds or more. Anything else? Want to keep it moving? Thank you so much. Appreciate it.